Right, hey. So welcome to the second lecture of Advanced Topics in Networking. So today we'll continue to speak about P4. So we'll continue to dive into the language, and we'll finish actually next week already with the language. And then it will be all for you to play with it during the rest of the semester and the project. So we'll continue this today. And we'll also see the first basic building block of this lecture as a technique, which is the label switching. And we'll see MPLS as one embodiment of the technique. So before I start, like a couple of quick announcements. So hopefully the audio delay is a little bit better today. So we actually completely changed the setup once again since last week. And I'm actually introducing a fake delay between the audio and the video right now, around 300 milliseconds, to hopefully make things a little bit equal. If it is not perfect, please let us know, and I can actually adapt this live so that hopefully the sync is a little bit better. Of course, in the recording, this is less of a problem because I can edit this, but still, I would like the live experience to be as good as possible. So keep us posted, and please give us feedback about whether it works better than last week. So that's for like setup and Zoom related issues. The second thing I would like to mention, and Romain already also sent this to you by email, but it's important that you also join the Slack workspace if you haven't done it yet. So this is very good for, like, for instance, during the exercise sessions, to reach out to the TA, ask questions live and get quick feedback. So please do register yourself there. We see that the student count is not as high as it should be. So clearly there are some of you missing. So you can find the URL on the Moodle, on the website. I'm sure you will actually find it. With these announcements out of the way, let's do first a quick recap of what we saw last week. As usual, if you have ever had a lecture with me, you know that I do this all the time. And then after, we'll jump right into P4. So let's get to it. All right, so last week, we essentially started to motivate the lecture, and why I think this lecture is interesting, and I hope you agree. So as a quick reminder, what we will see and what you will learn about in this lecture is how do we optimize the performance, the flexibility, and the reliability of network infrastructures. More specifically, large-scale ones, so important ones, as I say, like the ISP, the data centers, the IXP, so kind of like critical network infrastructure. So I started to motivate this first from the point of view of you as a user of the internet, and why would you care actually about these metrics, for instance. And here, in a nutshell, what it's important to remember is that by default, by design even, the internet only provides best effort service. So the IP routers, they do their very best with what they have, but they cannot guarantee that your packets will actually reach a destination, or will actually be corrupted, or will be duplicated or lost, etc., or the delay with which these packets will actually propagate. So there is no guarantee on anything in the internet. Most of the time it works actually surprisingly well, but sometimes it actually doesn't, and these are the times where you actually want to do something about it. And so in this lecture, again, this is what we do. So that's for you as a user. And then I also told you that, of course, there is you, but there is also a network operator on the other side who tries, I mean, these people, they try to, of course, like provide the best service with the infrastructure they have. They also try, of course, to minimize their cost while trying to maximize their revenue. So classical like equation in this case. And so the challenges for operators is that they carry more and more critical services. So here is just one example of those, but like, for instance, Swisscom runs all the telephony, TV, and of course, internet services on top of IP technology nowadays. And it has been almost 3 years that this is happening. And I told you, when you start to carry critical services like telephony, you really need to be careful about the reliability of your network. So clearly there is no playing around anymore. You absolutely need to make sure that your network will converge fast when there is a cut. And if there is a cut and VoIP traffic, so voice over IP traffic, starts to collide with Netflix traffic, you want to make sure that you won't drop, let's say, telephony traffic over video traffic. So you need to make sure, you need to instruct your network, of course, to start to do this. So as you carry more and more critical services, you need to start thinking about that. Of course, not only do you carry more and more critical traffic, but in general, you carry more traffic overall. So it's always a challenge as a network operator, but because you need to kind of like balance this need for speed. So as you have more users, each of them having on average a higher user speed, and each of them consuming more and more content, of course, your traffic volume will increase. So it's all about trying to kind of engineer these traffic demands in your network the best way possible. So going beyond shortest paths, as I told you, while of course keeping in mind that at some point you will need to upgrade your network. So the techniques we will see in these lectures, of course, cannot do miracle. If you receive, I don't know, 100 gigabits per second, and you have a bottleneck in your network at 10 gig, there is nothing you can do. So, so this is kind of like beyond, of course, what is possible. But here, the idea is trying to do the best with what you have in the realm of what is possible, of course. So that's for the, so these were for the motivation. And then I told you that we'll see different techniques in order to solve this problem. And I told you that there were 6 different techniques: traffic engineering, load balancing, quality of service, multicast, VPN, and fast convergence. So we'll see all of them. And actually today we'll see kind of a building block that we'll use for solving many of those issues. As I said, label switching will be one. So it will not be a theoretical lecture per se, so it actually is going to be very practical as well. And I hope all of you started to play already with your own virtual lab with P4 last week, and of course we'll continue this week. So this week you will actually start playing with MPLS, and you will actually implement label switching in P4 and start to build this data plane logic for implementing label switching. And this, you will continue to build upon that in the rest of the lecture. So you will see how you can make this evolve as the weeks go by. And in addition to P4 exercises, there will also be exercises in virtual labs. And actually, I hope today I can make a demo. I will dedicate some time to this to make a demo of MPLS in an actual layer 3 network. So I will show you this a little bit later in the lecture. So for the programmable network aspect, what we'll play with in this lecture is P4. So P4 is, as I told you, a domain-specific language that describes how a switch should process packets. So that's what P4 really is. So it's actually a simple language, as you probably have seen already. And it's quite constrained language as well because of the way a switch works. And that's actually good. So that enables P4 program to actually run at speed as well. So today we'll continue to dive into this. And we'll continue actually to, I will start with this even, to finish your first P4 program. Actually, it's probably not the second because you already did some exercises, but which is actually programming an IP router in P4, like a very basic ones, of course. So we'll start with this in a minute. So this week, as I said, we'll continue to speak about the P4 ecosystem and the P4 language in general. So this will be like the first 45 minutes of the lecture. And then during the remaining 45 minutes, I will speak about label switching. Start to speak, I probably won't be done today. Next week will be the last 45 minutes on P4, where I will explain you how you can maintain state and build stateful application in P4. And then we'll continue with MPLS, traffic engineering, etc. All right, so now, as I told you, let's jump right back where we were like 1 week ago. So what I will do now is switch back to the slides of last week and quickly finish the first example. And then after, we'll continue with the ecosystem. So let's go back to where we were 1 week ago with IP forwarding in P4. So as I told you, if you look at the forwarding aspect of a router, so not the routing aspect, not the control plane, but the data plane. So what does a router do when it receives an IP packet? And essentially, it's actually pretty simple. You need 4 actions. You, of course, need to look up what is the next step you need to use. So if you receive an IP packet, where should I send this packet next? You need to update the MAC addresses. So the packets will move from one link to another. So you need to make sure that you keep the link layer addresses in sync with where the packet will go next. You need to decrement the TTL. So it's not impossible that the packet is currently trapped in a loop because I'm sure you remember from your introduction lecture that loops can happen in a network. So if a packet is trapped in a loop, you want eventually this packet to disappear. So that's why you need to decrement the TTL. And of course, you need to also instruct the switch that if the TTL hits 0, that you want to drop it. This is also something you need to do. And then finally, of course, you want to forward the packet on the appropriate output port. So 4 different actions, and each of these actions, we actually need to encode them in P4. As I told you, P4 is all about the data plane, so what is going on in the forwarding logic, not about the control plane. So this you will also play with, but this will be normal algorithm, like routing algorithm that you will need to implement, for instance, in Python or in C. So what we look at though more, at least in the first part of the lecture, is the data plane logic. All right, so that's for like what the router does, these 4 basic operations. And then if you need to implement this in P4, if that's a question, then you need essentially to program 4 parts in P4. So there is this parser, that's the first part you need to program, the match action pipeline, and then the deparser. So again, like what is a parser doing is just extracting the headers that you care about from the packet. And you need to extract all the headers that you need to modify or read for your application. So if you think about it, if I'm building an IP router, I need to extract, of course, I need to extract the IP header. I also need to extract the MAC header, so the link layer header. So I need the MAC addresses, of course, to be extracted as well. So I will need actually to code in my parser that I want to extract these fields. Since I'm basically building an IP router, I don't really need to extract anything about the transport layer. I don't need the UDP layer, the UDP header, sorry, I don't need the TCP header either. Of course, if you're doing something more fancy like a NAT, then you would also need to go there. But in this basic example, we don't. So I instruct my parser to extract the right headers. And then once the switch, which runs my P4 program, actually runs this program, it will extract all these. And these headers will then be sent through a match action pipelines. And this is where the forwarding logic will happen. So this is where, for instance, you will change the header, you will change the source MAC address, the destination MAC address, you will adapt the TTL, etc. You will also, using the destination IP, you will perform a lookup to figure out where to send the packet next. So this is what you do in the pipeline. And then finally, in the deparser, you kind of like re-serialize a packet out of the headers that may have been modified, like the MAC addresses in our case, and the existing IP addresses that do not change in our example. And then you, of course, need to append to all of that, to all these headers that you deparse, you need to append the payload of the original packet. So this is also something which is actually done for you in the background. And then the packet gets out, of course, on the port that you instructed the switch to send it to. So really, this is kind of like the idea of what P4 does for you. So I already told you this, parser extracts the headers, match action pipeline implements the logic, and then the parser packs everything together. So that was what we saw last week in code, how these different pieces look like. So you have like the parser, then the control logic and the deparser, and then you have these main methods that glue everything together at the ends of the file. So this is typically what the P4 program will look like in reality. So in terms of the match action pipeline, I told you, you essentially define a control flow. So you need to define precisely as a control flow, what is the sequence of steps that you need to apply on these packets as they progress through your pipeline. So there will be, for instance, actions that you need to perform on these packets, and you might also need to look up in tables. So very frequently, you will actually do both. So in terms of the control flow, it's simple. It's an imperative program, usually very simple because we're doing simple operations in a switch. And what essentially we do is describing how the various headers and metadata will be modified by our pipeline. So here, there was also a question on Slack, I think today, a little bit earlier, about the difference between headers and metadata. So I want to perhaps like go back to this 1 second. So as I told you, the headers, these are typically the state that comes on the packet. So like the IP source, the IP destination, source MAC, destination MAC, TTL, all these information are on the packet, they enter the switch and you want to extract them. So this is what we mean by headers, things that are on the packet. These headers will be turned into variables and they will go through your pipeline and you can do things with them. You can read them, you can modify them, etc. So this is like the first type of information you can play with in your pipeline, the headers. The second type of information you can play with are the metadata. So metadata is extra data that comes on top of the header and that you can use, for instance, to maintain, let's say, partial computation reasons. So to give you an example, which is probably very simple, but give you, I hope, the gist. So let's say you want to build an application that modify the source IP for whatever reason. But the logic of your application needs to not only modify the source IP, but also remember what was the original source IP that was there before. So what you can do typically is actually use a metadata for that. So you will declare that you want to maintain in your metadata a 32-bit address, which is an IP address. And then you will copy the original IP in this metadata. And then this metadata, they will be carried over in your pipeline. So as your packet follow your switch. And then you can actually modify the header itself, which will be the value that will be actually be put on the final packet, which will be deparsed and then sent out. So I hope you see the difference already. So these extra information are not written on the packet itself. They're actually carried over next to the packet, but are very useful nonetheless. And the metadata, you can define them yourself. So there are user-defined metadata. And there are also, let's say, standard metadata. And these standard metadata, they are defined actually by the switch architecture. And typically, they will be related to extra state that comes with the packet, but are not written in the packet again. Typically, for instance, to give you like 2 examples, the timestamp at which you have received the packet. So of course, it's not written in normal packet, but the switch will actually will pre-populate, if you want, for you, a standard metadata that contains the timestamp. That's very useful, for instance, to compute the inter-packet arrival time. So between 2 packets, P1 and P2, you can do actually a computation that compute how long has elapsed between the 2. And then you can change the forwarding state of your switch, for instance, accordingly. That would be why you want to use that. A typical other metadata, standard metadata, is the input port. So you might actually, for instance, want to modify the behavior of your program according to where is the packet coming from. So that's another example of metadata. So I hope it's clear that you have headers and metadata. Both of them you can actually define yourself. And for the metadata, there will be also on top of all that standard metadata that come with the architecture. All right, so you have all these things that you can essentially play with in your control flow logic. So this is again what you see on this slide. You see that essentially we, for instance, in this case, we modify a metadata, which is the egress spec that contains where you want the packet to go. So that essentially is a metadata that instructs the switching logic in the switch to say to that logic where you want the packet to go next. What is the next port this packet should be sent to? And here, for instance, was changing the source address, the destination address, and we're also decreasing the TTL. So that's for the control flow. In the control flow, you can do actions, of course. So it's actually a good practice, I think, to try to isolate and, write modular code in general. It's always a good practice. So it's good to try to essentially group together the actions that semantically go together. Like for instance, here, IPv4 forward. So instead of having all this blob of instructions in an apply statement, it's better to extract it and create a kind of like a method, if you want, which is in this case IPv4 forward, that takes 2 parameters, a MAC address and a port, and then essentially perform the same action as before. And then you can just apply this action in the apply statement. That's kind of like a little bit easier to write and also for you to reason about. So it's kind of like good practice, but the original slide, the code on the original slide would have worked as well. So these are for actions, and now tables. So tables, so this might be a little bit tricky to understand. And these go back to the kind of like difference between control plane and data plane, as I told you last week. So again, like we are in P4 thinking about the data plane, okay? And if you think about the router, you have like one of the key pieces of a data plane router is the forwarding table that maps IP destination prefix to an output port. And so this is actually a table. So in P4, you will define the shape of that table. You will actually say that there is a key that is the destination prefix, and you want to actually match on this key using a longest prefix map logic. And then once you have a match, you want to say that the action that corresponds to that will actually be to send the packet to the corresponding next step. So if you want these kind of like tables, they map together a key that you define with an action that you define as well. but you only define the structure of the table. You don't define the content of the table in P4 because the content of the table is actually not pre-populated. The content of the table is populated by the control plane at runtime. So when you will launch your switch, your P4 code with a table in it, by default, the table will be empty. And then the control plane can, through an interface, which is built automatically, you can actually populate the content of the table. So for instance, you can say that 10/8 should go on that port, 11/8 should go on that port, etc. That's kind of how the control plane then tweak the behavior of the switch. So I hope that is clear, and this is important. So table is a diaplane construct, and in P4 you define the structure of the table, but the content of the table is actually populated by the diaplane. And this is actually what is illustrated here. And so, as I told you, a table has a key, and that key is actually one or more headers and metadata that you have extracted from your packet. So for instance, you can say that the key is the destination prefix or the destination address, or you can say that the key is the source MAC or whatever actually you want. And it could also be part of the metadata themselves. So you define what is it that you should match on, and then you define what is it that you want to do as an action once you have a match. These are essentially at least the two main things you need to define. You also need to define the size of the table, so how many entries you want to allow in this table, and a default action. So if there is no match, what is it that you want to do? Do you want to drop the packet? Do you want to forward the packet to the controller? Do you want to forward the packet on port 0? What is it that you want? But you can define the default action should you want to. You can also just drop the packet if you don't care. So as I said, you will define the structure of the table in P4. And so again, like there is a syntax to do that. It's something that you need to play with a little bit just to get like acquainted with that, but it's not very hard. So essentially you have the table name, you have a set of fields on which you can match, you want to match. There is a match type, longest prefix match, exact match, ternary match, range match. There are different type of matches you can use. Then there is a list of actions you want to apply, the size, and then the default action. And of course, if you want, for instance, to build an IP router, then you need to, as I said, you need a forwarding table, in this case, with 2 entries, for instance, that sends 123/24 left and 567/24 right. So we need to essentially build this table that enables us to do so. So it's actually pretty standard. So as a key, I told you this, we want to use the destination IP. So that's what we want as a key. The type of the match will be a longest prefix match, classical in IP forwarding. The action will be this IPv4 forward action we saw earlier, in which we will actually take a MAC and a port as parameter, and then, or drop. So by default, if there is no entry, we simply drop, which is actually the default behavior of a router. And that's how you would actually write it down in P4. So for instance, here we could define a new table, IPv4 LPM for longest prefix match. We match on the destination address, LPM as a match. We put our 2 actions. Let's say we use 1024 as the maximum entries, and then we drop by default. So this is kind of like working code, if you want, that kind of like defines very precisely what is the IPv4 forwarding table looking like in the diaplane. So the IPv4 forward action is just the same as before. So it just tells the switch, given a key, so given like a destination address, it will actually tell you what is the port, so where you want to send that packet next, and how to modify the destination MAC address accordingly. Note that you could also modify the source MAC address. You should normally, so it kind of depends how you think, how you allocate, let's say, the MAC addresses to different ports in your router. So you could actually, in P4, it's totally possible. You could just give, let's say, in this case, 1 MAC address for all the links. It's not super nice, but it works. But you can also, of course, here modify the IPv4 forward to also modify the source address accordingly. So that's how you do it. And then, as I told you, and that's really important to understand, is that you define this table, it's by default empty, and then the control plane, we use an interface, which is actually generated automatically, And then you can actually use this command like table add, for instance, from the control plane to actually start populating content here. And so here, what you will say is that you essentially add 2 entries in the table IPv4 LPM, and you are defining the IPv4 forward action on prefix 123/24, 567/24, and then you give the 2 actions, which is in this case to IPv4 forward. You give like the 2 parameters which are required, the MAC address and the port. And that's kind of it. So it's very, very simple in this case, but it works and does the job.
Laurent?
All right, so that's for the action pipeline for like a router. And then let's look quickly at the deparser. So the deparser.
Laurent, 1 second.
Oh, yeah.
We have a few questions regarding to the tables, table sizes. The first question is, what are the best practices for the size of different type of tables? And related to this, what is the point of setting a maximal number of entries in a P4 table, given that a table is populated by the control plane?
Okay, so these are great questions. So thanks whoever asked them. I'm sorry I cannot also track the question on the chat, but thanks Romain as well for relaying them. So the best practices for, let me talk to you as a human. So the best practices for the size of the table, and that's very much depend on your network actually. So if you are looking, for instance, at an ISP network, and you need to build an application like routing application, let's say you want to do internet routing, internet forwarding. So you need at least, as of today, there are I think 850,000 IPv4 prefixes that you will need to route if you want to carry the full internet routing table in your routers or in your switches. So this would actually guide your design choice. You know that you need to go at least that far. Actually, you need probably a little bit more because you want probably IPv6 addresses, internal prefixes, etc. So we are probably looking at around like 1 million entries there. Of course, if you are looking at building a very specific application, let's say for, I don't know, that does only layer 2 forwarding, then you probably don't need as many entries. So you will actually just see how many hosts you have and how many like MAC addresses you actually need to forward for. And then you will just adapt there. So there is no one good answer. I think what is important to keep in mind is that, of course, the resources of the switches are very limited. So you have around like dozens of megabytes of memory. And then, of course, if you put like 1 million for your IPv4 table, well, that will block you from putting more in other tables as well. So it's all about balancing essentially the resources across all the tables in a way that makes sense for you. So that's something that you need to do as a designer. So usually, typically, there is a context that comes with the application that enables you to answer these questions. So that was for the first question. What is the best practice for the table size? So now for the second question, which was, why do we actually give a maximum size and we don't just leave that empty? And then, as you folks said, anyway, it's the control plane that populates this thing. Well, there is a very good reason for that, is actually that you need to compile this program, you need to compile them to usually hardware. So you need actually this program to run in hardware. And the compiler needs to know what is the maximum size of the table in order to allocate the hardware resources that go with it. And if you don't bound that, then essentially that could be anything. That could be 10 million, that could be 10, and you do not know in advance. So that's why in P4, actually, a lot of the language is constrained so that the compiler can figure out in advance what is it that you want to do, instead of like discovering that at runtime. That, of course, can create some inefficiencies. And we have a recent papers actually trying to explore those, between the difference between, let's say, compile time information and runtime information. But at least in the context of this lecture, that's the reason. It's because the compiler needs to know how many entries you need in advance to allocate the resources for them. So that's why. So I hope I answered your question. If not, please feel free to ping Romain again, and then Romain will just chime in again. But thanks, these are very good questions indeed. All right, so now let's come back to the deparser. So the deparser is very simple logic. I think in the lecture, you won't I don't think you will play a lot with the deparser unless you go really fancy. But essentially in the deparser, you are defining the headers that you want to put back in the packet that will leave the switch. And so the input packet and the output packet might look different. So for whatever reasons, for instance, you might decide that you don't want to have the IPv4 header anymore. So the packet enters with an IPv4 header and then leaves without an IPv4 header. So you could actually do that very easily in P4 by, in the deparser, not including the IPv4 header that you have been extracting before. So essentially, the deparser idea is just that you will use this emit command to essentially just put in the final packet everything that you want. So typically you will do, as on the slide, you will emit the Ethernet header, the IPv4 header, and then the TCP header. Typically, if you are looking at TCP as well. If you don't parse, by the way, TCP, it will be part of the payload. So that's also something perhaps that I should stress. So you have the packet that enters, and then you extract the header using the parser. Everything which is not parsed is part of the payload. And as I told you, the payload will just kind of like move through the switch, but you won't look at it, you won't touch it in the pipeline, and then will be put back at the end with the headers and the payload. So if you don't parse the TCP headers, let's say, they will be part of the payload. If you parse them, they will be part of the headers, and then they will go through the pipeline. That's, again, like for you to start building a mental picture of what is going on here in the switch. Typically, though, you parse Ethernet. In most of the application, you will parse Ethernet IP, of course, and the transport header, and then the rest will be the payload. So that's kind of like classical. All right. So that was for like the last example, and actually I've given you already like a bunch of like, I think like extra information that I will be able to skip a little bit later. Now I would like to use the last, I hope, 15 minutes before the break to tell you a little bit more about the environment, the language, and then start MPLS. We'll probably run late, so I will do my best there. So first, the P4 environment. So let's look a little bit, if we think about the now P4 as an ecosystem. So not necessarily P4 as a language, no, P4 as an ecosystem. So the intuition behind P4 is that it should enable you to program many different kind of targets. So of course, like one target is a hardware switch, like the kind of switch we have in our lab. So the switches with like 32 ports, 64 ports, terabits per second of throughput. That's one of the targets you can write P4 program for. But that's only one. What you can do as well, for instance, is write a P4 program that you will compile and run in your network cards. So NIC, network interface cards. So you can, for instance, use P4 to define what is it that your physical card in your server, for instance, or in your laptop should actually do. And then the third example, actually I have 4 examples. The third example is, for instance, defining the forwarding behavior of your kernel. If you are running Linux, you can actually use P4 to kind of like, instead of using the Linux kernel to forward packet, you can use your P4 logic to do that. And then the final example, which is actually the one you will use in the lecture, would be to build a software switch. So a switch that switches packet actually as a software. So different type of targets. And so in P4, what they did in P4.16 is actually that they define this notion of target and of an architecture. So a target is kind of like a model of a hardware implementation. So you will have a model of a hardware switch, a model of your interface card, a model of, I don't know, like the Linux kernel. And then for each target, you will have an architecture that comes with it, which is essentially nothing more than an API to actually program against that target. So if you look as a developer, what you need when you program, you kind of like need the architecture model and a compiler. And of course, you need the target itself. So these things in yellow on the slide, these are vendor supplied. And then what you provide as a user, as a programmer, is of course a P4 program, and then the control plane logic as well that will interact with the target using an interface which is also generated by the vendor. So the architecture model, unfortunately, in the lecture, we cannot let you play with the switches. We would like to, of course, and I'm sure you would like it too. But it's just that the hardware constraint as such that it's actually quite hard to write a P4 program. It's possible, but it takes a lot of time because you need to learn about all the hardware constraints that come with it. So if you're interested though, I invite you to come to us and do a master thesis, a semester thesis, and then you can actually play with the switches because then you will have the time to learn about these things and really kind of like dive into it. In the lecture though, what we'll do is we'll use a software model. So we'll use this V1 model, which describe as a software architecture, something which is very close to PISA. So this is actually, PISA is the switch, the abstract switch architecture I mentioned in the first lecture that essentially corresponds to what we've been discussing so far. So we have like packet enters, there is a parsing stage, a sequence of match action. Then you have like queuing and buffering that happens, and then another sequence of match action, and then the output. So here, perhaps something I want to mention, because that's perhaps the first time that appears here. There is a difference between the ingress pipeline and the egress pipeline. So essentially what happens, if you think about the switch, packet enters on the port, let's say port 0, and then you parse it, you extract the headers, and then you can do a bunch of actions as a pipeline, tables, and do whatever you want there. And then at some point you need the packet to go on another port and to leave there. So that action of like moving from one port to the other, that's where the switching logic of the switch really happens. That is where you actually switch effectively. And then the packet gets out on another port, and this is where you can do a little bit more of processing as well. And that's the egress pipeline. So ingress pipeline before the switching happens, egress pipeline after the switching happens, okay? So that's kind of like something to keep in mind, that there are this in reality, and certainly in hardware as well, you have this distinction between ingress and egress. All right, okay, so that's the architecture we'll use. Each architecture, clearly this one, but also the ones like hardware architecture, like our switches, they define the metadata they support. As I told you, there are standard metadata, and there are also intrinsic metadata. Okay, so these are not user defined, so these come with the architecture. So standard metadata, these are the ones that are included in the P4 specification. So these are on the left-hand side of the slides. So these, any target will implement those. You know that they are there. And then on the right-hand side of the switch, you have the intrinsic metadata. These are the ones that depend on typically the architecture. So for instance, this particular architecture will have a metadata ingress global timestamp and egress global timestamp, giving you the clock cycles when the packet entered the ingress and the egress. But not all the architecture actually provide you with this. All right, okay, so these are for the metadata. So another thing which is kind of like very relevant in practice is the notion of extern. So what is an extern? Is essentially kind of like an extra building block that you can call from your P4 code, but you don't need to implement that block. So it's typically an external functionality, and the only thing that you can do is interact with it as a black box, but you cannot program it in any way. And the reason this is there is that depending again on the architecture we're talking about, there are different ways to implement, let's say, basic functionalities. Like, I don't know, performing checksum typically would be an example of an extern. So there are different ways. Of course, you wouldn't implement a checksum function the same way in hardware than in a software target. So that would be like a typical example of something that you cannot really express in P4 directly because it's very much architecture dependent. So think of extern and basic functionalities whose implementation is architecture dependent. So what we do in P4 is that we make this essentially, an extra building block, and then we just interface with it. Yes, so think of that the same way as Java interface. You have like the specification of the interface, you know what the parameters are, you know what is returned to you when you interact with that, but you do not need to provide the implementation. So typically what you will see as extern are registers, hash functions, and checksumming, these kind of things. So a register is actually the way to access the memory of the switch. And so that's something we'll see next week, is how do we build a stateful application? And we do that using registers. And again, it's quite, I think, easy to understand that if you are looking at an ASIC or like an FPGA or like a software switch, the memory that these devices use is of course very different. And so that's why you cannot really abstract this away and represent that in P4. So what we do is just we have a register like method, and then the different architecture can implement this differently. All right, so different architectures, different metadata, different externs. So this is, for instance, by the way, if you are interested, this is like a net FPGA. So that's another example of a P4 target. So this is actually an FPGA, which is tuned for networking applications. And you can see here on the connection side, you have like SFP connection, so optical connection. And then you have like the FPGA is a Vertex 7. So it's not the latest one, but it's still okay. And essentially that thing can talk P4 as well. So you can actually program the behavior of that board in P4. We do have 2 of these boards in the lab. So if you are interested, I would actually invite you to do again like a thesis, and then you can play with this. I'm sure some of you in the room, virtual room, will be interested into that. As I mentioned, these boards, they will provide you with different metadata in this case. All right, so that's for the environment. Let's now talk about the language a little bit.
Laurent, we have a few more questions.
Yep.
So first question relate to the deparsing that we talked about a bit before.
Yep.
The question is, if you mentioned that we don't necessarily have to parse the transport layer, the headers, like the TCP headers, yep. But that doesn't prevent another switch later in the pipeline to do parse and process this information.
Correct. Yes. Yes. So definitely. So you think about like a network, you have a sequence of switches. And so you can do you can have different programs on each switch that look at different things in the packets. So one might actually perform a routing decision based on the IP address, while another one might perform a load balancing decision based on the transport header, like the TCP, source port and destination port. So it's definitely possible to do that, yeah.
And another question is, how do we parse IP headers when we use VPN?
When we use what?
When we use VPN.
When we use VPN. Okay, so I will answer that question directly as we dive into the language. So indeed, depending on the sequence of headers and extra headers that you put before or after, then you need to do. Of course, you need to instruct the switch how to parse an IP header with a VPN label on top of that. So that's something we'll see together in a few minutes. Yeah. Any other questions?
Not so far.
Okay, good. Thanks. So let me switch back. I still have a few minutes to start the language, continue with the language, and then after we'll do a quick break. All right. Let me do this. Okay, so now I want to speak about the language. I want to kind of like dive a little bit more into the language construct and essentially dive a little bit more into this picture that I've been like explaining already quite a bit. So first thing first, I would like to start with the basics of the language and talk about data types, operation, and statements. And so something which is quite important here to keep in mind is like, again, like P4 is very, very limited. So it's not like your typical programming language where you can do things like, I don't know, multiplication or like floating point computation. So things are limited in the sense that, I mean, why do we limit this in P4 is that, again, the idea is to design applications that can run very, very fast. And we only have so many cycles actually to forward the packet between the input ports and the output ports. So there are like crazy amount of limitations that will kind of like, that you will need to work around in order to implement your logic. But as I said, so far we've always been able to work around them. Okay, my switch doesn't work anymore, all right. Okay, so the basics though, data types, operation, and statements. And we'll quickly go through that and then we'll do the break. So just give me 2 more minutes and then we'll do the break. So first, the base types. There are quite a few, and here again, like it's best for you to look in the specification what they are. But just to give you like the main ones, of course you have like Boolean values, true, false, bit string of a given width. So like, I don't know, bit strings over 10 bits, 12 bit, 32, 64, etc. Integers, so signed, you have plus or minus. Variable bit string length. So you can have a bit string that can have a length which might change. So typically here, the usage, for instance, is when you parse IPv4 options. So you do not know in advance how many options there will be. And so you need something variable because it might be, I don't know, 5 options, 3 options, 1. And so you do not know at compile time. So at compile time, just say, okay, it will be between X and Y. You also have variables to describe the match kind, errors, and then you just have a void one. So here, something that I want to stress, because it's important, of course, in practice, you don't have float, you don't have string. So you cannot do floating point computation, you cannot do anything related to string as well, unfortunately. So other things you can have besides the base types is the operators to build new types. And so here, what you will see a lot are operators regarding headers. So because again, this is what we do in Diaplane, we start by parsing these things. And so we'll actually play with headers. So for instance, this is how you define a header using the header command. And then you essentially define the component that will be part of that header, like a 48-bit destination address, 48-bit source address, and a 16-bit ether type that will say whether it's IPv4, IPv6, or whatever coming after. That's kind of like how you declare a new header. And then when you actually, so when you use the extract feature from the parser to actually parse the header out of the packet, what the parser will do, if it is successful in parsing the header, it will set a bit to true, which is a validity bit. So in that header, if you want, there are these 3 fields: destination address, source address, and ether type, and there is also a validity bit. So sometimes in your application, it's actually useful to look and test whether the validity bit is 1 or 0. So that actually tells you whether the thing was parsed correctly or not. And I will finish with this before the break. But in addition to a header, you have a header stack and a header union. So header stack, very useful. And we'll see this actually, you will see that in the exercise. And this just defines not only one, let's say, one Ethernet address, but an array of one Ethernet header, but an array of Ethernet headers. So sometimes you can see this in some layer 2 networks where you can have more than one, let's say, VLAN tags. So you can have an inner VLAN tag and an outer VLAN tag. Or in the case of MPLS, you can have multiple MPLS labels. Or in the case of a VPN, you can have multiple VPN labels. So here what you can do is essentially define a stack. So a sequence, an array of labels. And all these labels, they will have the following structure. So 20-bit of label, 3-bit of TC, etc. So essentially, that's how you define a stack. And what you need is, because as I said in P4, you need to tell the compiler how much resources it will require at runtime. So here you need to define the size of the stack. So here will be up to 10 MPLS headers in a row. And then the header union will be the last thing before the break. The header union is just telling that, for instance, an IP header, it's either an IPv4 packet or an IPv6 packet, but it cannot be both. So you cannot have an IPv4 header mixed with an IPv6 header. It's one or the other. And you can actually define this kind of, you can capture this notion that it's either one or the other using a header union. So you know that you will have an IP header. It's either going to be a v4 header or a v6 header. All right, so let me stop here and let's make a break. So it's 3:04. So I propose that we resume at 3, let's say 18, 19, so that we continue. We have quite a packed schedule, so let me stop now. So we resume in 15 minutes. And feel free to ask questions again using the Slack and then the chat or the Slack, and then I will answer them back after. You can all hear me again and hopefully see me again. So yeah, okay, thanks, Romain. So we'll continue now for the remaining 40 minutes. I won't go through the entire P4 language part. I won't have the time, but you actually don't need it for the exercise as well. So I will just go perhaps briefly through what I can for the next 5-10 minutes max, trying to highlight the main aspects that are important for the lecture, for the exercise, sorry. And then after I want to switch to the label switching part, which actually will be relevant a lot for the exercises. It's more important that we do that today. So let me switch back to the slides and then explain you a little bit more where we were. If I can switch back, okay. All right, so still little gotchas with the setup. Sorry. All right, so I was telling you before the break, header, header stack, and header union. So these are three derived types in P4. So you have like the base types and the derived types. So you can essentially, with the operators to derive types, you can build bigger types out of smaller ones. You have also, like in C, if you have ever played in C, you probably are familiar with struct and a tuple. So you have the same notions in P4. So a struct is a collection of named member, and then a tuple is a collection of unnamed member. So you will see this a lot, especially, for instance, when you define metadata, you will use a struct typically. And then you have like plenty of others. So again, like the goal is not for me to kind of like just go through the spec like one in slides. I think you will discover that as you make programs yourself, you will see more and more of the different types. So that there is like enumeration as well. You can use type specialization so that you can define new types if you want, etc., etc. So all of this, again, like the URL is below. Probably when you do the exercise, it's good to have the spec open so that you can actually check it out in real time. But it's all about just figuring out also the syntax of P4. But a lot of it is kind of known from previous programming language. As I told you, what is important to keep in mind, though, is that P4 is very limited in terms of the operations you can do. So you can do plus, minus times, but you cannot do division, you cannot do modulo, for instance. So this is not allowed. You cannot do floating point computation either. So that's kind of like limiting. Of course, you can approximate it, but you will have to, that's the best you can do. So for instance, you can approximate the division by bit shifting. Of course, you can do logical operation. So again, the not, or, and, bit shifting. Again, you can do bit slicing, concatenation, all of these you can do, but no division, no modulo. Of course, you can have variables as well. You can define constant. So that's the same as in a normal programming language. I think though what is important to keep in mind is that these variables that you define and that you see in P4 code, they're actually ephemeral. So you will have them. It's a little bit like you need to think about these variables as being instantiated whenever there is a packet that enters your switch. So the packet enters, and then the variable will take the value that you have indicated in your code, and then the packet will leave, and then the variable will be kind of like destroyed. So the lifetime of a variable is really only the processing time of the packet. So a variable, what it's mean technically is that the variable, you cannot use it to actually maintain state across packets. So what you need there is actually to use a register. And I told you this before the break, but the register, you need to go through this extern to actually access the memory of the switch there. So that's kind of like already perhaps important for you to keep in mind. So variables, very useful. Of course, they make your code also more readable. So please do use them. But keep in mind that if you have like a count, for instance, that you do +1, you initialize a counter to 1 and you do +1, the next packets will have the new counter initialized to 1 as well. So it won't be kept across packets. So again, if you want to use this, you need to use a stateful construct, and there are like a few in P4. All right, so clearly the switch doesn't work anymore, so I have to do it manually. So the two stateful constructs we'll see next week. Well, one you already saw actually, it's the tables. So that's a stateful construct, and the other one is the one we'll see next week, is the extern one. Okay, then again, I will be brief here, but it's, I think, all pretty classical, but I'm sure you know what return means in a normal programming language. It's kind of like the same thing in P4. Exit, same stuff. If else, yeah, of course you can do if else. You can do also switch and have cases. So all of these, I'm assuming you know already from one programming language or the other, and the semantic is essentially exactly the same. So it's pretty, you won't be lost here with those instructions. So that's, so that's for the, like, let's say the basic types and operations you can do. The parser, I think what is important for me to stress, and I will just be brief here, and that's something you will actually use right now in the exercise, is that you can, okay, here, you can have loops in the parser. So if you remember last week what we saw this, is that the parser, you define the parser as a state machine in a sense. You have a starting state, an accepting state, a reject state. And then you essentially instruct the switch to jump from one state to the other according to essentially the bits that are being seen at the beginning of the packet. So Ethernet, IPv4, TCP, UDP, etc. So you can see it's not the case in the state machine on the left-hand side, but you can have loops in this state machine. And so typically you will have a loop, for instance, when you have a stack. And so again, since we will see and talk about label switching, in which we can have multiple labels in a row, then you will have to use a loop in the parser. So that's, again, it's just a principle that you need to know that, okay, you can do that. And you will actually see the syntax together with the TA right after in the exercise session. So I really, of course, invite you to attend the exercise session there so that you will get this firsthand. All right, okay, the rest, I think it's pretty, let me just quickly check that I'm not forgetting something super important for the exercise. I don't think so, yes. So, okay, let me do one thing, and then I will start with MPLS. So as I said very early in the lecture, I mean, okay, P4 is not just something that you can use to program a router. It's nice, but it's not the most exciting thing in the world. But P4 really enables you to take control of what the switch does. So you really take control of forwarding logic, and you actually have the ability to run that logic at insane speed, so terabits per second. So you have only a few nanoseconds between packets. This is what it means. And so it enables you and us essentially to kind of like build new applications. And also for us as a researcher, it's very interesting because now we can finally test our ideas and implement them and run them at line rate. So at, again, like terabits per second. So I just would like to take like 2 minutes to just like mention a few of the works we've been doing recently. Also trying to motivate you perhaps to actually knock on our door after the lecture and do a project with us. So some of these projects actually have been done with students who took the lecture. So let me do that quickly now. So how do we use P4 in our research? Well, that's the first paper I would like to mention is this one. It's a paper from Albert and Alex, both of whom are TAs of the lecture. So if you're interested, you can feel free to chat with them about this paper. So in this paper, what we show is that we can not only, with, let's say, P4 gives you access to the forwarding logic. So like these pipelines that link essentially the ingress pipeline with the egress one. But what P4 doesn't enable you to do is take care of the scheduling and the queuing logic that sits in between. So if you think about it, if you think about a Tofino switch, for instance, so a Tofino switch, that logic is hardwired. So you can program, when the packet arrives, you can program what you do before you switch, and then you can program what happens after. But what is happening here is essentially kind of closed. And so what we did in this paper with together with Albert and Alex is kind of like show how we can take control of that as well, and how we can program even the middle part. And so that is like a nice work that actually runs also on the Tofino, so on the actual hardware switch. So take a look at the paper if you are interested in looking at this. Another work that we did recently is about fast conversion. So this is like one of the topics we'll see in this lecture. So we use P4 to actually show that we can converge very, very fast, not only upon local failures, like a link goes down next to a router, it's in your network. So you can actually converge fast in this case. So that's what we'll see in this lecture. But what we did with Thomas and Edgar and Maria, who are also all TAs in this lecture, is that we kind of like generalize this technique to also remote failures. So these are failures that are far away from you. So think about it. For instance, let me switch back to me. I'm here at ETH and I'm sending a lot of traffic towards, I don't know, like Google, for instance. And we might go via 2 or 3 networks between ETH and Google. And so there can be a failure anywhere between me and Google. And so what we do in this paper is essentially we use the P4 switch to actually keep track of statistics in real time about how do the TCP flows behave. And whenever there is a failure remotely, of course, they will be lost, there will be packet loss, and then TCP will start to retransmit. And so what we do here, we kind of like build a P4 application that can capture this retransmission and then detect that there is a failure and then trigger a reconvergence. So that's kind of like generating, if you want, a failure signal by analyzing in real-time TCP statistics. All right, so with this, so what I was saying is that we build a P4 program that essentially analyzes these TCP signals in real time and can detect failures. Another paper, another use of P4 is to actually protect applications against DDoS attacks. And so one of the applications here that we looked at is Bitcoin. So probably you do not know that, but Bitcoin is actually subject to kind of like network level attacks. And so what we showed is that there is actually a way to kind of like offload the logic of some aspect of Bitcoin into the switch, and so that we can actually run it in hardware and not be actually subject to any DDoS. And then the final example, I think, yeah, okay, not final example, okay, a few more examples. Another one from Edgar. Is how do we speed up the network computation? So here it's a paper where we show that we can use P4 to kind of like run actual computation. So here it's perhaps a little bit counterintuitive, right? I just told you that P4 is very limited. So here what we do in this paper is that despite the limitations, we actually show that one can run a routing protocol inside the switch. And so what is very nice is that essentially that routing protocol runs at hardware speed. So nanosecond level if you want. And so of course it's very interesting from a speed aspect. So you can actually start building very interesting things on top of that. So that's like a recent paper we had. Another example which relates to security is that we can actually use P4 and the logic there to kind of like obfuscate the kind of like topology. So imagine, for instance, you are in a network, let's say, I don't know, a bank, and you would like to protect your network from like eavesdropping attack. So like perhaps inside attackers that are trying to figure out what does the network look like by looking at the network traffic. So here what we do, essentially, we use the P4 programmability capabilities to obfuscate the topology at runtime. And so the cool thing here is that we can do that without kind of like impairing the performance of the network at the same time. And then that's the final example. So you see that there are plenty more examples in the pipeline that I cannot speak about. But this one is related to somehow to machine learning as well. And it's kind of like to show that one can also use the P4 programmability aspect to actually implement fancy classification algorithm directly into the switch. And so here, essentially what we do is that we kind of implement like a machine learning algorithm, which is like a random forest, if for you, those of you who know, and we can run it directly in the switch. So we can train this algorithm and then run the classifier that comes out of it directly in the switch, again on terabits per second. That's kind of like what we do. All right, okay, so sorry for the interruption again. And let me now start, in the last 25 minutes I have, let me start to speak about MPLS enabled switching. So just to give you the idea and the gist of it, and then you will actually start implementing that in the exercise. So please do make sure that you attend the exercise as well, and that you really try to do them, because otherwise it will be very tough to do the projects and also the exam. So it's important that you do the exercises. All right, so let's jump right into it, and let's talk about label switching. So let me switch here, oops. All right, so before I speak about label switching, I would like, because label switching, you can think of it as a hybrid between packet switching and circuit switching. So packet switching, these go back to like probably the first lecture we had together for those of you who had like the introduction to communication networks with me. I told you that in packet switching, essentially what we do is that we break up the data we want to send into tiny pieces. We slap an address on top of each of them, an IP header, and then we send this packet independently from the other. And then each packet will travel independently in the network, and each router in the middle will look at the destination address and perform a routing and a forwarding decision. And the routing and the forwarding decision is kind of like local. So you are a router, you receive these packets. Each packet is independent of the other. And then what you are doing, using these routing protocols in this forwarding state, is figuring out what is the next stop you will send the packet to. That's kind of like the idea of like packet switching. Everything is packet-based, all these packets are independent, and you don't maintain any state about TCP connections, for instance. It's all, the only state you maintain is the forwarding state, that prefix, that port. That's what you do, essentially. That's for packet switching. So circuit switching, that's also something we saw together. In circuit switching, it's a little bit different. So in circuit switching, the source will first establish a connection through the entire network to the destination. So there will be a signaling mechanism, a signaling protocol that will be used in order to essentially establish this connection. And then all the routers or the switches in between. In this lecture, by the way, router and switches, they will be merged because as you, I hope, realize now, in P4, you can implement a router, a switch, a layer 2 switch, a layer 3 router, a layer 4 load balancer, all together in the same device. So it's kind of like blurry. We call them, let's say, network switch in general, not normal router and layer 2 switch as we do in other lectures. Okay, but so coming back now to the circuit switching aspect. So you kind of like signal a connection in the entire network, and then you communicate over that connection. And then when you are done, the source essentially stop the connection. So stop the connection, yes. So what is nice with this is that you can actually have guarantees. So I mentioned to you the best effort is not great because we don't have any guarantee because packets can collide, there can be congestion. And because of that, we cannot really get any upper bound or lower bound about the performance we'll get. So in circuit switching, this is not the case. So in circuit switching, when you actually build the connection, you can also reserve some bandwidth. So for instance, you can reserve, let's say 10 gig per second as you are building this connection. And then, at least in the pure circuit switching, this connection is really dedicated to you. So you are the only one who can use this 10 gig per second per se. So that gives you actually like some guarantees. So you can really have bandwidth guarantees and predictable performance there. Another thing that this enables you to do is it also enables to build switches that are that simple. So, okay, there is a little bit of logic to signal these connections together, but the actual switching, right, is very basic because it's all connection based. So you kind of like know where the connection enters and leaves, and that's the only thing you need to know. So you don't need to do like an IP prefix lookup, for instance, or language prefix match. You essentially look at connection and then you immediately know where the connection should go. And again, what is important is the connection is initiated by the source to the destination. Okay, so there's really this kind of like notion of end-to-end, if you want, that doesn't really appear in normal packet switching. Of course, that's also something we saw together. The problem of circuit switching is that it's inefficient if you don't use all the bandwidth you are requesting. So if you request, let's say 100 gig per second, because you can send up to that point, but you almost never send 100 gig per second, you are wasting bandwidth for nothing. And also, you need to wait a little bit at the beginning just to establish essentially the connection in the first place. So that's also something which is annoying. So you can see here, I hope that circuit switching has some advantages, notably in terms of like predictability, but it also has some pretty damn big disadvantages in terms of scalability and like the time it takes to actually scalability, because you have to maintain this state for the connection, the time it takes to establish these connections, and also the wasted bandwidth that you have. So what we'll talk about in this, in the context of MPLS is kind of like an hybrid mode. And so as usual in hybrid, we try to get the advantages of one solution or like multiple solutions without the disadvantages of either. And so that's something that we'll try to achieve here as well with this notion of label switching that relates to virtual circuit. So here, the idea behind virtual circuits, and MPLS is kind of implementing that idea, is that we will establish connections, but we won't establish physical connections in any way. We will actually establish virtual connections. And we will establish this connection on top of an existing network. So that means that in practice, there can be many virtual circuits, virtual connections that will go over the same link. So that's kind of like related a little bit to, if you think about it, to TCP connections. Many TCP connections can go over the same link, of course. But the cool thing here is that we can kind of like modulate, if you want, the kind of guarantee we give to these connections by playing, for instance, with how many of these connections we put on each link. So we can actually kind of like fix the path, at least with some protocols, we can precisely figure out the path where we put these connections there. And then us, by kind of like modulating the amount of multiplexing of these connections we have on each link, we can kind of like get absolutely no guarantee. So if we put all the connection everywhere, nothing, I mean, no fanciness whatsoever, we end up defaulting to best effort. And if we, of course, like place carefully each connection on different paths, then we end up with like physical guarantees in terms of like the bandwidth each of these connections can have. So it's kind of like the idea that we can go with whatever trade-off we want, but at least we have the ability to kind of like play. Instead of just getting best effort with IP, here we will be able to play a little bit more, which will be interesting, of course, for many applications. Okay, so in what we'll see though in our lecture, there will be many similarities, as you will see. So we'll use these virtual connections, many similarities between packet switching and virtual circuit. So the idea will be that now the packets that will carry this connection ID, if you want, and then the switch will just look at the connection ID and then decide where to send the packet next according to this connection ID. And then all the tricks will essentially be what kind of like connection ID should we use and where do we send them in order to get some kind of like properties out of the network. That's essentially what we'll want. Okay, so actually let me start with MPLS really per se. So as I said, MPLS is kind of like, it's a way to implement virtual circuit in an IP network. So it's again like, it's about trying to get the best of both worlds. It's trying to get the, let's say, fanciness and kind of like guarantee capabilities we can have with circuit switching and virtual circuits with like the flexibility of IP in general. That's kind of like what we try to combine together. And then the core ID, and that's kind of like basic, you will see, is just that we'll have a label, an extra label, and we'll insert that label between layer 2 and layer 3. So we'll have the Ethernet layer, then we'll have this MPLS label stack, and then we'll have the IP header. And so that's why you will often see that MPLS is referred to as a 2.5 networking protocol. But it's not really layer 2, it's not really layer 3 either, it's somewhere in between. So it actually doesn't fit perfectly in the Aussie stack, but that's okay. And MPLS is used a lot. So in practice, you use it for traffic engineering, QoS, fast reroute, and VPN. So it's really like a building block we'll use a lot in our lecture. Okay, so now switching slides again. So you can see, by the way, these slides come from a different source. So here they actually come from my PhD advisor. So that's some of these slides I used as a student like you when I was learning about this way back. So let's talk about MPLS and label swapping. So as I said, in MPLS, now we are looking at routers and switches that will not base their forwarding decision based on the IP address anymore, but based on labels. And so on packet arrival, what you will have is packet arrives, and then a router will actually perform a lookup about the label, and then figure out where to send that packet according to that label. So you can see here, on packet arrival, the router analyzes the packet label and the input port. So you can have the input port playing a decision as well, playing a role as well in the decision, and then deciding where to send that packet next. So for instance, here you can see the first example of an MPLS network in which, for instance, you have like this router 1 here that has a forwarding table, which is label based. And then you can see that, for instance, if traffic arrives from the west port with a label A, then the router or 1 will kind of like forward that packet on the east port with an out label X. So this label here will be sent. So when packet is received with this label, it will be sent here, and then the label will be swapped there to X. So that's already kind of like kind of like a first thing to notice is that you will look at the label, and then you can also flip the label as the packet propagates. So the packets will have a label, enters, and then can be swapped as it goes through multiple hops, and then will leave the network. And then the label, of course, will be removed because your host, your smartphone, my laptop doesn't understand these labels. It's only used within the network. So as I said, though, MPLS is about integrating this kind of idea of label swapping with IP. So we'll see now how they integrate together. So MPLS is used in IP networks, and you will see why, because they are very useful in this context as well. But so what we have then is you have IP packets that enter your IP network, let's say on the left-hand side here of the slide, and IP packet that exit your network on the right-hand side of the slide. And then you can see in the middle, you have this MPLS label networks. And you can see already these kind of like connections here, like you can see here, flow 1, flow 2, flow 3. These are 3 connections in the sense of a virtual circuit I was mentioning before. And then, of course, since we are looking at IP packets on the left and IP packets on the right, that means that, and label packets in between. So we need to kind of like slap this label on the packets somewhere. And so that's why we'll actually define some specific roles for the router. So there will be the routers that are sitting at the edge of the network, like RA and RB. These are, they will be known as label edge router. So these are routers that set the labels on IP packets. So the packets arrive without a label, and then they leave this router with a label. Then you will have the routers in the middle, like SLR 2, 1, and 3, or RC in this case. And these routers, they only look at the label. They don't care about the IP address anymore. They only look at the label. And then, of course, at some point, the packet will reach the edge of our network and then will exit our network. And these routers will remove the labels so that we retrieve pure IP packets. And those will refer to them as egress LSR. And LSR being a label switching router. So, okay, so essentially, that's kind of like important. So in this MPLS network, you have like routers at the ingress, they put the label in, routers in the core only look at the label, they don't need to look at the IP address anymore. Routers at the egress, they remove the label. Okay, so that's kind of like, I hope, intuitive enough so far.
Laurent?
Yep.
One question. You mentioned before that the routers could swap labels. What is the interest of swapping label within an AS?
Yeah, so that's a great question. So it's essentially for scalability purposes. So that's something I will explain in a minute. But if you don't, of course, you can not swap and then keep the same label within the AS. But then that means that you need the label to have like network-wide meaning. So for instance, if you have 1 million connection, you need each of the connection in the entire AS to have like a dedicated ID and be unique. So that might be a problem of scalability. So if you swap though, you can actually avoid this problem of explosion because of course these connections, they don't go everywhere. So what you can have is actually you can reuse labels and swap these labels around in different parts of the network. So that's the answer to that question, the short answer is scalability point of view. So by using swapping, we'll go from network-wide label space to a local device-wide label space, or per interface even label space, and that scales a little bit better. That's the answer. That's a good question.
And other question is, can a router inherit all the 3 specific roles that we just saw all at the same time?
Yeah. Great question. The answer is yes. So you can definitely, for some of the connections, be the ingress, for other connections, be the egress, and then for yet other connections, be transit router in between. So that's definitely the case. So you can be different rows, but it will be for different connections. For the same connection, I guess you might be the ingress and the egress, but in a sense that you don't need label swapping. So that's also something we see. In that case, you don't really need the label at all. The packet enters and leaves via you directly. So the packet enters via one neighbor and leaves from you to another neighbor. You don't need label there at all. So technically, you could see yourself as an ingress-egress router, but in practice, you don't really play any role in terms of labels there. But otherwise, as I said, for different connections, the answer is definitely yes.
And there is one more question. Does it mean that the router needs to know the topology of the network in order to use or to know how to swap the labels?
That's an excellent question, and the answer depends on the protocols that are used to signal these labels. So we'll actually dive into that. So all these questions, we'll answer them in the rest of the lecture, even though I won't have the time to finish. But most of the label distribution protocols, right? So you have a protocol that distributes this label in the network. They are indeed somehow aware of the topology. And so one way to get aware of the topology is to actually listen to the IGP protocol. So the routing, intra-domain routing protocol, typically OSPF, for instance. So these protocols, and especially the one we'll see together soon, they actually directly tap into the topology knowledge to figure out actually how to propagate these labels and to compute them in the first place. So yes, you need to be somehow topology aware, but the router is somehow topology aware as well, right? So when you look at the OSPF as a routing protocol, a router knows the entire graph. So depending on the protocol, of course, you are not always topology aware, BGP being a good example. You only know the destination and the path, not the entire topology. But inside your domain, typically you can be and are topology aware. Yeah, this is also a good question. Any more questions?
That's all for now.
Okay, yeah, thanks. So please keep them coming up. Okay, good. So we need to solve 3 problems, and I would like still to do the demo so that I can show you a real MPLS network. So I will just take 2-3 minutes to actually explain a little bit here the label and the behavior of ingress and egress router, and then do a quick demo. And then you will start to dive into the exercise. For the exercise, I think what is important anyway to know is that it's label-based operation, label-based switching. So you use labels, you don't use the address anymore. And then you will see why it is useful as well in the exercise. So the label in MPLS, it's a 20 bits label. So you can have 2 to the 20 different labels, which is embedded in a header, which is 32 bits long. And as I said, you can have a stack of this label that will be coming later. So one label, one MPLS label, it's 20 bits long, embedded in 32 bits MPLS header. This is important, the operations you can do on these labels. So as I said, at the entrance of your network here, RA and RB, you will typically do push operation. So push meaning that you will push a label on top of the packet that doesn't have a label, for instance. In the core of the network, you will perform swap. And there was a question about this, why do we need the swap? As I told you, it's for scalability reasons. But essentially, a swap operation can enable you to turn a label into another one. Of course, and that's actually the case on this slide, you can see here, LSR 1 and 3, they are swapping the label for the same value. That's totally okay. So you can have a label entering with 21 and a label exiting with 21 as well. In which case, you effectively keep the same label in the entire network. So it's not because there is a swap operation that you are forced to swap. You can or can not change your value. And then when you leave the network, you perform a pop. And so pop means that you remove the label. And you can see here that this push and pop, of course, this terminology have not been picked randomly. It's because we're talking about a stack of labels. So you can push on top of the stack, you can pop. And so this is really where it comes from. Okay, so content of the forwarding table of an MPLS router. Well, of course you have the label that enters. So you have an in label, and then that's the label of the incoming packets. Then you have the next stop. So that is where you actually send the packets that are arriving with this label. So typically it's an outgoing interface, but it could also be the router itself. So this is actually sometimes interesting to send the packets to the router, instructing the router that it needs to process it further And so typically we see that this is the case when there can be multiple labels that are slapped on the packet. So could be either an outgoing interface, let's say, or the router itself. So let's leave it there and we'll be clear later. And then you have an operation that you can perform on the label. So you can swap, push, or pop. That's essentially what you have in the forwarding table. So that was the, okay. So let me actually give you the demo. I think it's going to be a little bit more, visual, let's say. So here I have like actually running a virtual lab with this topology running there. So you can see like 5 routers, R1 to R5 that are connected together. They belong to the same AS1. And you can see that there is one prefix which is attached to the AS, 130.104/16. And then I've given one loopback address to each of these routers. So 130.104, 10.1, 10.2, 10.3, etc. Then I've activated MPLS in this network. And that network is actually running here. And so you can see I'm connected to each of the 5 routers. And the first thing I can show you is that I'm running MPLS. So I've configured the routers to actually have MPLS. And of course, I can show you the forwarding table here, which is an MPLS forwarding table. So you can see here already what I was telling you about, that you have like, kind of like depending on the destination IP. So for instance, this loopback address here. So this loopback address is actually the address of R5. I'm connected to R1, as you can see here. And so router R1, when I'm sending an IP packet to the loopback address of R5, it will actually use 24 as an output, as an outgoing label. So that means that then 24, so packets with the label 24 will be sent to R2. So now what we can do is look in R2. If you do a show MPLS forwarding table, you can see that the incoming label 24, which is here on the left-hand side, local label. So that's kind of like incoming label, if you want, the equivalent of it in the Cisco terminology. So you can see that 24 will actually be swapped. So here it will change to 21 and will be sent on the interface fast Ethernet 10, which happens to be this one here. So we start here in R1. The outgoing label is 24, reaches R2, and then R2 takes 24, turns it into 21, and then blasts it to R3. And then if we go to R3, what is it that we see? It's already here. You can see, so that incoming label 21 will actually be popped. So we will remove them, and then we will send them to interface 10, which happens to be R5 directly. So this is what is happening. A label is put, is swapped, and then is removed in R3, and then R5 receives an actual IP packet without a label at all. So let me finish here this lecture by just capturing the traffic which is going on over here on this interface between R1 and R2, and actually showing you the label being put there using Wireshark. So hopefully that will work. So I will capture here, and then I will try to open Wireshark, if I may. Yes, so I hope you can see that. So now I'm capturing traffic here between R1 and R2. So I will first just filter here for ICMP traffic. And then I will actually launch the ping here. So I will go back to R1, and then I will ping this IP address over there, which happens to be the loopback interface of R5. You can see that it works, which is always good. And we can now look in Wireshark again. And here you can see the packets. So here, what you can see, this is the first packet that R1 has sent. And you can see indeed that there was this MPLS header there. So you can see that it's a 2.5 protocol, in the sense that you have the Ethernet header here, the IP header over there, and then you have this MPLS header here. And you can see that the outgoing label is 24. And so that's essentially working. It shows that it's working. And then I will just perhaps finish by showing you this. So this is the request that R1 sends to R5. And that's the answer that you receive from R5 back to R1. As you can see, is the ping reply over there. And here you can see that there is no MPLS header, which is weird. But actually, perhaps you have seen this already. But so what is going on here is that when you send the request, so there is a label here between R1 and R2, there is a label between R2 and R3, and then R3 will pop. So R5 will receive a plain IP packet. Then R5 will receive a plain IP packet, will answer to the ping, and then we'll put, as an answer to the ping, we'll put a label here between R3 and R5. There will be a label here between R2 and R3. And then R2 will actually pop that label before sending back the packet to R1. So this is exactly why you have a label when you get out, when you send the packet out, but not when you receive them, because it happens that when you receive the packet, the previous router has removed them. And so this is actually called penultimate popping. It just means that the penultimate router, so R2 in this case, on the return pass, will remove the label for you so that you don't need to do that on R1. So we'll see, we'll of course dive more into this later. All right, so I will finish here. I'm sorry I lasted a little bit longer. There were some glitches still with the setup, so I guess we need to improve further. That's fine. Again, please do make sure that you now join the exercise session where you will actually implement like an MPLS data plane. You will actually play with these labels, push, pop, swapping, this penultimate popping as well. So you will actually see this firsthand. You will actually implement this in P4. Next week, we'll continue to see MPLS. We'll actually see these protocols you have been asking questions about that need to know the topology. We'll look at this in detail. And we'll also continue in P4. So the program will continue to be quite heavy, but I hope it's not too fast. If it is too fast, or like you feel that we are going too fast, please just let us know as well. We always, as I said, welcome feedback. All right, thanks. So I will stay connected for like a couple of minutes if you want to ask questions by voice, for instance, or through Romain, it's fine as well. Otherwise, see you next week, same place. Yeah.
So we do have a few questions that appear during the demo. First, a technical simple one is the demo you showed the Cisco IRS router.
Yeah.
Okay, so that was easy. Other question, it seems that we can push multiple labels to the same packet. Is that correct?
It is correct, technically, yes. In the examples I've shown, though, we only push one label. So perhaps I see what was the reason the question was asked is that there is a local label and an outgoing label. So strip local label and replace that by incoming label. So essentially, if you receive an incoming label with 24, then what you do is that you swap it to 23. And that's essentially how should you read this table. But as you can see, it's always either I'm popping, so I'm removing one label and then it becomes an IP packet in this example, or I'm swapping one label for another. But I don't push, at least in this example, I've never pushed more than one label at a time. Yeah. But it can happen in practice.
But that would be possible, right? You could.
That is definitely possible. And we'll see this next week for sure. And I think you will even see that in the exercise. And this, again, is very useful for many applications, but also for scalability purposes. Yeah.
Another question is, why do we need the IP address when the MPLS table, in the MPLS table, well, we could just route on the labels themselves?
Yeah, so it's an excellent question. So why do we need the IP address? It's because any of these routers that I'm showing you here on the picture, they can actually act as an ingress for, let's say, like this IP, this loopback address 130.104.10.5, right? Let's say that that's the destination we want to send label packet to. Packets can enter everywhere, right? They can enter in R1. I've done a ping from R1, so of course they enter from R1. I can do a ping from R2, they will enter from R2, ping from R3 and R4, they will enter from there. So as I told you as well, MPLS is a virtual circuit technology. So the source needs to establish a connection, if you want, to the destination. And here, the connection is kind of pre-established, but this would be for next week. So what is important here, though, to keep in mind is that the source needs to know what is the destination and where is the destination connected to in order to figure out the label. And so that's why, if we look in this output here, you can see that actually a label is often associated to an IP prefix that identifies the kind of like destination that can be reached through that connection. So this is kind of why you see this, in this example again. So that's again something we'll see together. I wanted to see this next week, but I couldn't. But that's why. And so there is a mapping really between IP and labels. That's why MPLS, I've told you, it's kind of like IP meets virtual circuits. So the two are really kind of like entangled together. And that's where notably one of the mapping appears in practice. But yeah, excellent question. I just couldn't actually cover it yet. More questions?
That is all for now, as far as I've been made aware of.
Okay, good. So as usual, though, feel free to ask your questions on Slack as well or in the forum. So you know where these medium are. And with this, then I will see you next week for the next session where we'll dive more into this. I hope exciting technologies for you. Yeah. See you then.